This discussion is the continuation of the lecture which we have discussed in lecture 14. In lecture 14, we have started to understand the behavior of the electrostatic fields in material medium. More specifically, we have started to study the electrostatic field in conductors, and we have seen in the last lecture that is the conduction current and the convection current. Now we are going to see the behavior of the electrostatic fields in conductor. So let us start our today's discussion. Here first we have the conductors, and we know have an abundance of charge that can freely move. That means this is the characteristics by which we can understand the material is a conductor. Now suppose we have an isolated conductor, or we can say a piece of conductor, that is the isolated conductor, and this isolated conductor is placed in an external electric field EE. Here the EE is representing the external electric field. Now when this isolated conductor is placed in external electric field, the positive charges inside the conductor are pushed along the direction of the applied electric field, while the negative charges will move in the opposite direction to the direction of the external electric field. So this charge migration, that is the positive charge migration and the negative charge migration, takes place very quickly, and these free charges do two things. First, they accumulate on the surface of the conductor and form an induced surface charge. Second, the induced charges set up an induced or internal induced field EI, which cancels the external applied field EE. So this leads to an important property of the conductor, and this important property is that a perfect conductor, that means the conductor whose conductivity is infinite theoretically, cannot contain electrostatic field within it, because the internal electrostatic or induced internal electrostatic field will be in the opposite direction to the direction of the external electric field. So inside the isolated conductor, the total electrostatic field will be 0. So a conductor is called an equipotential body. What is the meaning of that? Means that the potential is same everywhere in the conductor. So this is based on the fact that E equals to minus grad V, because this E here, E is equals to 0 inside the conductor. So here del dot V equals to 0. So ultimately what we will get is that V is equals to 0. So everywhere the voltage difference or the voltage you will get, actually the voltage difference V1 minus V2 or V2 minus V1 also will be 0. That means V2 minus V1. So from that we can say this conductor is equipotential body. So in another way we can understand this one by considering the point form of the Ohm's law, that is J equals to sigma E. Now to maintain this J is the finite current density, that is the current density. To maintain that current density finite for a perfect conductor, that E must be 0 because sigma is infinite. So to make this J finite, this E must be 0, so that we can get J equals to, or J is finite current density. So in other words we can say E will tends to 0 because sigma or the conductivity will tends to infinite in a perfect conductor. Now inside the conductor the electrostatic field is 0. Now if we apply some charges, or if we introduce some charge in the interior of such a conductor, then the charges will move to the surface and redistributed themselves quickly in such a way that the field inside the conductor vanishes. So ultimately, we can say if we apply some extra charges inside the conductor, then also the electrostatic field inside the conductor will be 0 always. So, and according to the Gauss law, if E equals to 0, the charge density rho v must be 0, because we know that del dot D equals to rho v according to the Gauss law. So del dot D means del dot epsilon E equals to rho v. Here epsilon is a constant, so del dot E equals to rho v by epsilon, and here E is equals to 0, so rho v must be 0. So the charge density inside the conductor will also be 0. So from that we can conclude, or from the discussion we can conclude again, that a perfect conductor cannot contain an electrostatic field within it. So under static conditions, E will be 0, rho v will be 0, and VAB is 0 inside a conductor. Now let us take another condition. In this condition, we have considered a conductor whose ends are maintained at a potential difference V. That means a battery or a source of EMF is connected across this conductor. So in this case, that electrostatic field inside the conductor will not be 0. Now the question is why? Here you note that in this case E is not equals to 0 inside the conductor. Now what is the difference? Actually why? The answer is there is no static equilibrium, since the conductor is not isolated but is connected to the source of electromagnetic force through wires, which compels the free charges to move and prevents the eventual establishment of the electrostatic equilibrium. That means the equilibrium will not be, that is the conductor will always having the potential difference across this conductor, and it will not be equilibrium at any time. So for that, so in this case of the figure, above figure we have seen, the electric field must exist inside the conductor to sustain the flow of current. Now as the electrons move, they encounter some damping force called the resistance. Now based on the Ohm's law, J equals to sigma E, we know, we have seen. So now we are going to derive the resistance of the conducting material. Now suppose the conductor which we have considered here, this conductor has the uniform cross section S and the length L. The direction of the electric field E produced inside the conductor is same as the direction of the flow of positive charges. So the flow of positive charge, the direction of the flow of positive charge will be same as the direction of the electrostatic field inside the conductor, because no equilibrium is present for the second case, for this case. So positive charge will move in the right hand direction. So electric field also will be in this direction, same direction. And the current also will be in the same direction. So this direction is opposite to the flow of electrons, that we know. Now the electric field is uniform and its magnitude is given by this E equals to V by L. So this electric field, the magnitude of the electric field can be calculated using the potential difference V by the length L. Again, we know for a conductor of uniform cross section, the J, that is the current density, is equals to I by S. Now we are going to substitute the equation 9.1, this expression, and equation 9.2 to the expression 9.3. So here J is equals to I by S and J equals to sigma E, and this sigma E can be written as, you see that E can be replaced by V by L, so sigma V by L. So from that equation 9.4 we can find out that V by I, so V by I equals to R, so R equals to V by I, and that is equals to L by sigma into S. So this 1 by sigma can be written as rho, that is the resistivity. So R equals to rho into L by S, that we know, that is known to us. The resistance of a material is equals to rho, that is the resistivity, into the length of the material and the cross section divided by the cross section of the material. And this equation is useful to determine the resistance provided the cross section of the material is uniform. So when the cross section of the material is uniform, then only we can apply 9.5, expression 9.5, or R equals to V by I, and to calculate the resistance R. But if the cross section of the conductor is not uniform, then also we can use R equals to V by I, but this resistance, equation 9.5 R, that is equals to rho into L by S, we are not going to apply. In this case, the V can be written as the VAB, that is equals to minus integration of A to B E dot dl, that we have seen earlier in the earlier discussion. That V will be replaced by this equation, and I also we have seen in the last lecture, that is the surface integral of J dot ds, or J means sigma E. So this R can be calculated for non-uniform cross section of the conductor. R equals to V by I, or by the expression 9.6 we can calculate the resistance. Here in this expression 9.6, you can see that the negative sign is omitted. Now why that? Why we have not written here negative? The answer is given here. You can see that the negative sign before V, which is equals to minus of integration V dot dl, is not given because integration of E dot dl will be negative if I is positive. So I is positive we have taken. So the integration of E dot dl is negative. So negative, negative, positive. That is why this negative sign is not given. Now we have calculated the resistance. We have seen also the behavior of the electrostatic field in a conductor when it is connected to the EMF source, and when the isolated conductor is placed in the external electric field. Now we can also calculate the power P when the conductor is connected to the battery, and this power is defined as the rate of change of energy W in joules, or this power can be defined as the force times velocity. So here this power in watt is equals to volume integral of rho v dv E dot u. Now how we are getting that? You see that volume integral of rho v dv, that means equals to q. For the q charge, for the volume of charge, the total charge enclosed by the volume, we know that the volume integral of rho v dv. So rho v dv equals to q, and we know qe equals to force F equals to qe. So here QE, that means force dot U, because it is the vector quantity we are taking, the vector product, that is the dot product we are taking, because it may happen the force and the velocity of the charge may not be in the same direction. That is why we have taken dot. But if it is moving in the same direction, then cos theta is 0, so it will be 1, no problem. So that is why P equals to volume integral of rho v dv E dot U, that is equals to volume integral of E dot rho v u dv. So here rho v is the constant, so we have multiplied this rho v in with the u, because we want to write this expression rho v into u for the convection current. We have seen this is the current density. So actually this is the expression of the current density. So P ultimately we got equals to volume integral of E dot j dv. Now this is known as the Joule's law, and we have studied Joule's law, but this is one of the form of the Joule's law. Now we can find out the power density, that is Wp, which is in the term that is watt per meter cube, and which is given by taking the derivative of this capital 9.7 with respect to the volume. So from that we can find out the power density. So here Wp equals to d dv of p, and that from that we can find out E dot j, and j equals to sigma E. So sigma into mod of vector E square. So that is the power density 9.8, which is showing the power density. Now you can see that for a conductor with uniform cross section, if the cross section of the conductor is uniform, then dV will be equal to ds into dl. ds is the cross sectional area into the length dl, so we will get the volume dV. So by putting this expression here in expression 7.9, we will get that expression P equals to, you see that line integral of, because dV if you take, then that is ds into dl. So if you take the integration for all the side, so it will be volume integral of dV. So here surface integral of ds, a line integral of dl. So from that, if we apply here, we will get P equals to line integral of E dot dl into volume integral of J dot ds. Sorry, here it will be S surface integral of J dot ds. So here surface integral of J dot ds equals to I, and line integral of E dot dl equals to V. So P equals to V into I, and that form P equals to Vi is familiar to us. From that we can get P equals to I square R. So this equation is more common form of the Joule's law in electric circuit theory. So now we are going to see the polarization in dielectrics. That means up to the point here, up to this point, equation 9.9, we have completed the behavior of the electrostatic field in conducting medium. Now we are going to see the behavior of the electrostatic field in dielectric medium. So before that, we want to see some properties of the that is the material, dielectric material. First we are going to see is the polarization of the dielectrics. Here 3 points we want to discuss, or 5 points. You can see that actually the 3 basic points, from that we will understand how the dielectric material becomes polarized, that we are going to see here. So first point here shows that we know the main difference between a conductor and a dielectric lies in the availability of the free electron in the outer shell to conduct current. That we know, the availability of the free electrons. From that we can understand it is a dielectric or it is a conductor. Now the charge in a dielectric are not able to move freely because they are bound by finite force, because it is a dielectric, so charge is not free. But we can certainly expect a displacement when external force is applied. So to understand the macroscopic effect of an electric field on a dielectric, suppose we have an atom of a dielectric that is containing a negatively charged electron cloud, and a positively charged nucleus at the center. Now since the amount of the positive charge and the negative charge is equal, so the whole atom, or we can say molecule, is electrically neutral. Now if we apply the electrostatic field to that atom or the molecule of the dielectrics, then the positive charge is displaced from its equilibrium position or the center in the direction or in the same direction of the electric field. That means if we apply the electric field to an atom of the dielectric, the nucleus will uh, move, or it will be displaced from the center of the molecule towards or in the same direction as the electric field, the direction of the external electric field, by the force F plus, that is equals to QE. Similarly, the negative electrons or negative charges will move in the opposite direction of the applied electric field. So by the force F equals to QE. So due to this displacement of charges, a dipole is formed and the dielectric is said to be polarized. So whenever we are applying the external field, the positive nucleus will be displaced from its equilibrium position in the direction of the external electric field, and the negative charges will be displaced in the opposite direction of the applied electric field, and this will produce the dipole, and we can say that the dielectric material is polarized now. Now in polarization state, the electron cloud is distorted by the application of the electric field E. Now this distorted charge distribution is equivalent by the principle of superposition to the original distribution plus a dipole whose dipole moment is P equals to QD. You know the dipole moment we have seen earlier, that how to calculate the dipole moment P, that is P equals to QD, and here the D is the distance from the minus Q to the plus Q. But this distorted charge distribution is equivalent by the principle of superposition that is given here. You see that when the external electric field is not applied to the atom of the dielectric, this is the picture. Now we have applied the external electric field and it will try to force the nucleus along the direction of electric field, and the negative charges will move along the direction opposite to the direction of the external electric field. And from that we can get the equivalent diagram of dipole plus the original distribution. So this diagram we will get from the superposition of the original distribution plus this dipole. So now instead of only one electron or only one atom, if we have n dipoles in a volume del V, then the total dipole moment we can find out easily. You can see that Q1 D1 plus Q2 D2 and Qn Dn, from that summation of k equals to 1 to n Qk Dk. So if we have a small volume dV, inside that dV volume we have n number of dipoles, then the total dipole moment can be calculated by the formula 9.11. Now from this formula 9.11 also we can find out the intensity of polarization. That means if we consider the unit volume, so what will be the dipole moment at that particular unit volume, that we can find out, that is the intensity of polarization. And we can define the polarization, that means the intensity of polarization, by the small p. The total dipole moment is defined by the capital P, but the intensity of polarization is defined by the small p, and which is the unit is coulomb per meter cube, and that is the dipole moment per unit volume. And you can see that P equals the total dipole moment divided by del V. So from that we can get the dipole moment, total dipole moment per unit volume, and the volume sinks to zero. That means the unit volume, very small volume. So the limit is V del V tends to 0. Therefore, from this discussion what we can conclude is that the major effect of the electric field E on the dielectric is the creation of the dipole moments that align themselves in the direction of E, and this type of dipole is said to be non-polar. So what type of dielectrics are non-polar? The dielectric material in which there is no dipole, but when we apply the external electric field, the dipole is formed, and this dipole, the formed dipole, will orient themselves along the direction of the electrostatic field, and the material is called polarized, and this type of material or dielectric material is called non-polar material. An example is the hydrogen, oxygen, nitrogen, rare gases, all these examples of the non-polar material. So in the non-polar dielectric, when we apply the external electric field, the dipole is formed. But there are some other type of material called the polar dielectric material that we will see here. So non-polar after that. So here you see that non-polar dielectric molecules do not possess dipole until the application of the electric field, as we have seen. Now other types of molecules such as water, sulfur dioxide, hydrochloric acid, etc. have built-in permanent dipoles that are randomly oriented, and this type of dielectric are called polar dielectrics. Now the polar dielectrics are those, in these dielectrics the dipoles are built in, but these dipoles are randomly oriented. That is why it is not polarized. But when we apply the external electric field, these haphazard dipoles will orient themselves along the direction or parallel to the external electric field, and we will get the polarized material. So here, when an external electric field is applied to the polar molecule, the permanent dipoles experience a torque tending to align its dipole moment parallel to E. So we have the two types of dielectrics. One is non-polar dielectrics, another is polar dielectrics. In non-polar dielectrics, there is no dipole or permanent dipoles, but when we apply the external electric fields, dipole is formed or dipole will form and the material becomes polarized. But in the polar dielectrics, the dipoles are permanent, or it is built in dipoles are present in the polar material when we but it is in the random orientation. But when we apply the external electric field, the dipole moment will orient themselves parallel to the external electric field and the material becomes polarized. So that is all about the today's class, students. In the next class, we are going to calculate the electric field or electric field intensity due to the polarized dielectric. So this discussion will continue in the next class also. Thank you very much.